Introduction to Google Cloud Interconnect. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring Google Cloud Interconnect, which is Google's solution for establishing dedicated, private network connections between your on-premises infrastructure and Google Cloud Platform. This service is fundamental to hybrid cloud architectures where you need consistent, reliable, and high-performance connectivity between your data centers and the cloud. Unlike internet-based VPN connections that travel over the public internet, Interconnect provides physical, direct connections that offer significantly better performance, lower latency, and enhanced security. Understanding Interconnect is essential for architects designing enterprise-grade cloud solutions that require predictable network performance and data transfer capabilities. Google Cloud Interconnect comes in multiple flavors to accommodate different use cases, bandwidth requirements, and budget considerations. The service is designed to scale from small deployments needing just a few hundred megabits per second all the way up to massive enterprise implementations requiring multiple 100 gigabit connections. The key differentiator from traditional VPN solutions is that interconnect traffic never traverses the public internet. Instead, it travels over dedicated fiber connections, which means your data is physically isolated from internet traffic, reducing exposure to threats and eliminating the unpredictable performance characteristics of internet routing. The architecture we're examining today shows how Google Cloud Interconnect fits into the broader ecosystem. At the foundation, we have your on-premises environment, which could be a traditional data center, a colocation facility, or even edge computing locations. This connects through various interconnect options to reach Google's global network infrastructure. The connection terminates at Google Cloud regions where your virtual private cloud networks reside. This creates a hybrid cloud environment where workloads can span both on-premises and cloud locations seamlessly. The diagram illustrates three connection paths representing the different interconnect products. Dedicated Interconnect, which provides the highest bandwidth and performance. Partner Interconnect, which offers more flexibility in locations and bandwidth options. And the comparison point of VPN, which travels over the public internet. Each connection type serves specific requirements. Dedicated Interconnect is ideal when you need guaranteed bandwidth from 10 gigabits per second up to 100 gigabits per second and have proximity to Google's colocation facilities. Partner Interconnect is perfect when you need flexibility in bandwidth starting from 50 megabits per second, or when your facilities aren't near Google colocation points, allowing you to leverage service provider partnerships. The VPN option, while not technically interconnect, provides a reference point for internet-based connectivity that's useful for development, testing, or low bandwidth scenarios. Understanding these options and their trade-offs is crucial for designing the right connectivity strategy for your organization's specific needs. Dedicated Interconnect Overview. Dedicated Interconnect is Google's premium connectivity solution, offering direct physical connections between your network and Google's network infrastructure. This option is designed for enterprises with high bandwidth requirements and proximity to Google's colocation facilities. The term dedicated here is significant because it means you're getting physical fiber connections that are exclusively yours, not shared with other customers. This exclusivity translates to predictable performance, guaranteed bandwidth, and the highest level of network isolation possible. The bandwidth options for Dedicated Interconnect are substantial, starting at 10 gigabits per second and scaling up to 100 gigabits per second per connection. For organizations requiring even more capacity, you can provision multiple connections in parallel. This makes Dedicated Interconnect suitable for the most demanding workloads including large-scale data migrations, real-time data replication, high-frequency trading systems, media rendering farms, and any scenario where consistent, low-latency, high-throughput connectivity is mission-critical. Looking at the architecture diagram, we can see the complete flow of how Dedicated Interconnect operates. Starting from the left, we have your on-premises data center which contains your networking equipment, particularly your edge routers. These routers connect to what's called a colocation facility. A colocation facility is a physical data center where multiple organizations house their equipment in a shared space. Google maintains presence in many colocation facilities worldwide, specifically chosen for their strategic locations and robust infrastructure. Your equipment physically resides in this colocation facility, in a rack or cage that you or your organization controls. From your equipment in the colocation facility, you establish physical fiber optic connections directly to Google's networking equipment, which is also present in the same colocation facility. This is represented by the connection going to Google Edge. The Google Edge refers to Google's point of presence, which is essentially Google's networking hardware at the edge of their global network. This hardware is specifically designed to handle enormous amounts of traffic and provide the first point of entry into Google's private backbone network. The physical connection uses industry-standard networking protocols, typically single-mode fiber optics, to ensure maximum distance capability and signal quality. Once your traffic enters Google Edge through these dedicated connections, it travels across Google's global network. This is Google's private fiber network that interconnects all of their data centers, regions, and services worldwide. This network is one of the largest and most advanced private networks in existence, engineered for extremely low latency and high reliability. Your traffic never touches the public internet as it traverses this network. Finally, the connection terminates at your Google Cloud VPC, or virtual private cloud, in one or more Google Cloud regions. The VPC is where your cloud resources like virtual machines, databases, and applications reside. The Dedicated Interconnect provides a seamless bridge between your physical infrastructure and your cloud infrastructure, allowing them to communicate as if they were on the same LAN. Dedicated Interconnect Technical Requirements. Implementing Dedicated Interconnect requires careful attention to technical specifications and prerequisites. These requirements exist to ensure compatibility, reliability, and optimal performance of the connection. Understanding these requirements up front is crucial for project planning, budgeting, and avoiding deployment delays. The requirements span physical infrastructure, networking equipment capabilities, protocol support, and operational considerations. The first major requirement is physical proximity to a supported colocation facility. Google doesn't provide dedicated interconnect connections everywhere. They're available only in specific colocation facilities where Google has established a point of presence. These facilities are typically large, carrier-neutral data centers operated by companies like Equinix, CoreSite, and other major colocation providers. You must either already have equipment in one of these facilities or be willing to establish a presence there. This might involve renting rack space, installing equipment, and maintaining a physical footprint. The colocation requirement is non-negotiable for Dedicated Interconnect. If you're not in a supported facility, you'll need to consider Partner Interconnect instead. The second critical requirement involves your networking equipment specifications. Your edge routers must support 10 gigabits per second or 100 gigabits per second Ethernet interfaces. These aren't common speeds in traditional enterprise environments. They're typically found in service provider-grade equipment or high-end data center gear. The interfaces must use specific transceiver types, typically 10G base LR for 10 gigabit connections using single-mode fiber, or 100G base LR4 for 100 gigabit connections. The equipment must also support industry-standard routing protocols, specifically Border Gateway Protocol or BGP for exchanging routing information with Google's network. BGP is a complex protocol that requires expertise to configure and maintain properly. The diagram illustrates these key technical requirements organized into four main categories. Physical location requirements show that you need equipment in a Google-supported colocation facility, with rack space and power already provisioned. The locations are limited to specific facilities where Google has presence, which affects your geographic options. Equipment specifications detail the router requirements, including the supported interface speeds of either 10 or 100 gigabits per second, the specific transceiver types needed for fiber connections, and the mandatory support for BGP version 4 for routing. These aren't trivial requirements. They often necessitate equipment upgrades or purchases. Network configuration requirements specify the operational parameters needed. You need to obtain an autonomous system number, commonly called an ASN, which is a unique identifier assigned to your network for BGP routing. ASNs can be public, obtained from regional internet registries, or private for internal use only. You must configure Link Aggregation Control Protocol if you're using multiple physical connections for redundancy and increased bandwidth. Link Aggregation Control Protocol bundles multiple physical links into a single logical link, providing both redundancy and load balancing. The VLAN trunking requirement means your switches must support 802.1q VLAN tagging to separate different types of traffic across the same physical connection. Finally, the redundancy recommendations are critical for production deployments. Google strongly recommends, and most enterprises require, provisioning at least 2 separate interconnect connections for high availability. These connections should be in different colocation facilities if possible, or at minimum in different physical locations within the same facility, to protect against facility-level failures. Diverse fiber paths ensure that your 2 connections don't share the same physical fiber routes, protecting against fiber cuts or other path-specific failures. These redundancy measures are essential for meeting enterprise SLA requirements and ensuring business continuity. Partner Interconnect Overview. Partner Interconnect solves a critical challenge that many organizations face with Dedicated Interconnect: the requirement to have physical presence in Google's colocation facilities. Not every organization has equipment in these specific locations, and establishing a presence can be costly and time-consuming. Partner Interconnect addresses this by allowing you to connect to Google Cloud through a supported service provider who already has connectivity to Google's network. This creates a more flexible, often more cost-effective option for organizations that need dedicated private connectivity but lack physical proximity to Google's interconnection points. The beauty of Partner Interconnect lies in its flexibility and accessibility. Service providers participating in the Partner Interconnect program have already invested in the infrastructure to connect to Google's network at multiple locations globally. These providers offer you a connection to their network, and they handle the connection to Google on your behalf. This means you can establish private connectivity to Google Cloud from many more geographic locations than would be possible with Dedicated Interconnect alone. It also means you can leverage existing relationships with carriers and service providers you already work with, simplifying procurement and support. The bandwidth flexibility of Partner Interconnect is another major advantage. While Dedicated Interconnect requires minimum commitments of 10 gigabits per second, Partner Interconnect offers much more granular options. Connections start as low as 50 megabits per second and scale up through 100 megabits, 200 megabits, 300 megabits, 400 megabits, 500 megabits, 1 gigabit, 2 gigabits, 5 gigabits, and 10 gigabits per second. Some partners even support 20, 50, and 100 gigabit connections. This granularity allows you to match your bandwidth purchase to your actual needs, avoiding over-provisioning and controlling costs more effectively. It also makes Partner Interconnect suitable for smaller deployments and branch offices that don't require massive bandwidth. Examining the architecture diagram shows how Partner Interconnect introduces an additional network layer compared to Dedicated Interconnect. Starting from your on-premises data center on the left, your network equipment connects to a service provider network. This connection could be established in multiple ways: through an existing MPLS circuit you already have with the provider, through a new Ethernet connection ordered specifically for this purpose, or through a connection in a colocation facility where both you and the service provider have presence. The key point is that you're connecting to the service provider's infrastructure, not directly to Google's. The service provider network, shown in the middle of the diagram, is the provider's own backbone infrastructure. This could be a telecommunications carrier, an internet service provider, a managed service provider, or a cloud connectivity specialist. The provider's network has established partner interconnect connections to Google at multiple locations. These provider-to-Google connections are pre-established, tested, and maintained by the service provider. This is where the provider brings value. They've already solved the colocation and technical requirement challenges, allowing you to benefit from their existing Google connectivity. From the service provider's network, traffic flows through their partner interconnect connection into Google's global network. Once inside Google's network, the behavior is identical to Dedicated Interconnect. Your traffic traverses Google's private backbone without touching the public internet. The connection terminates at your Google Cloud VPC in the appropriate region. From your application's perspective, the connectivity behaves the same whether you're using Dedicated or Partner Interconnect. The difference is in how the physical connection is established and where the demarcation points are. With Partner Interconnect, you're responsible for connectivity to the service provider. The service provider is responsible for connectivity to Google, and Google is responsible for their internal network and your VPC. Partner Interconnect key features. Partner Interconnect's feature set is specifically designed to address the flexibility and accessibility challenges that organizations face when trying to establish private cloud connectivity. Understanding these features helps you evaluate whether Partner Interconnect is the right choice for your particular use case and organizational constraints. The features span geographic availability, bandwidth flexibility, cost considerations, and operational simplicity, each addressing specific pain points in cloud connectivity. The expanded geographic availability is one of Partner Interconnect's most compelling features. Because service providers can establish Partner Interconnect connections in many locations, you can connect to Google Cloud from places where Dedicated Interconnect isn't available. This is particularly valuable for organizations with distributed operations across multiple countries, regions with limited Google colocation presence, or those operating in emerging markets where cloud infrastructure is still developing. The service provider network serves as an extension of Google's reach, allowing you to establish private connectivity from your existing facilities without needing to relocate equipment or establish new colocation arrangements. Many enterprises find this especially useful for connecting branch offices, regional data centers, and remote facilities that couldn't justify the infrastructure investment of Dedicated Interconnect. Flexible bandwidth options represent a significant cost optimization opportunity. Unlike Dedicated Interconnect's requirement to commit to 10 gigabits per second or 100 gigabits per second increments, Partner Interconnect's granular bandwidth tiers allow you to right-size your connection. If you need 500 megabits per second, you can purchase exactly that capacity without paying for unused bandwidth. This granularity becomes especially valuable when you have multiple sites with varying bandwidth needs. You can provision a 5 gigabit connection for your main data center, 1 gigabit connections for regional offices, and 200 megabit connections for small branches, all using the same Partner Interconnect framework but paying appropriate amounts for each location's actual requirements. Looking at the diagram, we see the key features organized into 4 distinct categories. The flexible bandwidth category shows the range starting from 50 megabits per second for small offices or development environments, scaling through 100, 200, 300, 400, and 500 megabit increments for medium workloads, then jumping to 1, 2, 5, and 10 gigabits per second for larger deployments. Some partners even offer 20, 50, and 100 gigabit options for enterprises with massive bandwidth needs. This flexibility means you can start small and scale up as your cloud adoption grows, avoiding large upfront bandwidth commitments. The multiple locations category highlights that hundreds of service provider locations exist worldwide where you can establish Partner Interconnect. These aren't limited to the specific colocation facilities required for Dedicated Interconnect. Service providers operate in major metropolitan areas, secondary markets, and even some remote regions, giving you far more options for where to connect. The service providers themselves number in the dozens, including major telecommunications carriers like AT&T, Verizon, and BT, cloud connectivity specialists like Equinix and Megaport, and regional providers serving specific geographic markets. This variety means you can often work with providers you already have relationships with, simplifying procurement and ongoing support. The lower entry cost category addresses budget considerations that affect many organizations. Because you're not responsible for colocation costs at Google's facilities, not purchasing high-end 10 or 100 gigabits per second capable equipment, and not meeting Google's direct peering requirements, the overall investment to get started is substantially lower. Your costs typically consist of the circuit to your service provider and the monthly fee for the partner interconnect service itself, which is often charged per megabit or in bandwidth tiers. For organizations with limited capital budgets or those wanting to test cloud connectivity before major commitments, this lower barrier to entry is compelling. Small and medium businesses, in particular, find Partner Interconnect more accessible than Dedicated Interconnect from a financial perspective. Finally, the simplified setup category explains operational advantages. The service provider manages the connection to Google, handles the BGP configuration on their side, manages the physical infrastructure and redundancy, and provides a single point of contact for support issues. From your perspective, you configure your connection to the service provider using familiar technologies, then work with the provider to establish the partner interconnect attachment to your Google Cloud VPC. The complexity of interconnecting with Google is abstracted away by the service provider, allowing your team to focus on application connectivity rather than infrastructure management. This operational simplification often translates to faster deployment times and reduced ongoing management overhead. Interconnect bandwidth comparison. Understanding the bandwidth options across different interconnect types is crucial for capacity planning, cost estimation, and architecture design. The bandwidth you choose directly impacts performance, costs, and the types of workloads you can support. This comparison helps you understand not just the raw numbers, but the practical implications of each bandwidth tier and which interconnect product delivers which capacities. The bandwidth landscape divides into three distinct categories based on the connectivity method. Dedicated Interconnect operates at the high end of the spectrum. Partner Interconnect covers a wide range from small to large, and VPN serves as the comparison point for internet-based connectivity. Each category has specific use cases where it excels and scenarios where it would be inappropriate. The key is matching your requirements to the right service tier. Examining the table in detail, we see Dedicated Interconnect offers two bandwidth options, 10 gigabits per second and 100 gigabits per second. These are the only choices, there's no middle ground. The 10 gigabit option is suitable for enterprise workloads with substantial data transfer needs, such as regular database replication, large file transfers, or moderate-scale application traffic. In practical terms, 10 gigabits per second can transfer approximately 1.25 gigabytes per second, meaning you could transfer a terabyte of data in roughly 13.5 minutes under ideal conditions. The 100 gigabit option is designed for the most demanding scenarios, large-scale cloud migrations where you're moving petabytes of data, real-time video processing, high-frequency trading requiring microsecond latencies, or massive distributed applications with constant inter-cloud communication. At 100 gigabits per second, you're moving 12.5 gigabytes per second, capable of transferring a terabyte in just over a minute. Partner Interconnect's bandwidth options show remarkable granularity, starting at 50 megabits per second and progressing through 11 distinct tiers. The 50 to 500 megabit range serves small offices, development environments, disaster recovery connections, and applications with modest bandwidth needs. A 50 megabit connection, while seemingly small, can transfer about 6.25 megabytes per second, which is adequate for dozens of users accessing cloud applications, light data synchronization, or backup operations for smaller datasets. As you move up through 100, 200, 300, 400, and 500 megabits, you're accommodating more users, more concurrent applications, and larger data transfers while still maintaining cost effectiveness. The 1 to 10 gigabit partner interconnect tier bridges the gap between small office connectivity and enterprise-scale deployments. A 1 gigabit connection delivers 125 megabytes per second, suitable for regional offices, medium-sized application deployments, or departmental cloud initiatives. The 2 gigabit and 5 gigabit options serve growing deployments or multiple applications sharing the same connection. The 10 gigabit partner interconnect option matches Dedicated Interconnect's lower tier in raw bandwidth but with the operational flexibility of working through a service provider. Some organizations choose 10 gigabit partner interconnect even when Dedicated Interconnect is available, preferring to leverage their existing service provider relationships and avoid co-location management. For very large partner interconnect deployments, some providers offer 20, 50, and 100 gigabits per second options. These aren't universally available across all providers and locations, but they fill a crucial niche for organizations that need dedicated interconnect level bandwidth but want the operational model of partner interconnect. A company might choose a 50 gigabits per second partner interconnect connection to consolidate multiple regions or business units onto a single high-capacity link while maintaining the simplified management model of working through their carrier. Cloud VPN appears in the table as a reference point rather than an interconnect option. VPN connections typically support up to 3 gigabits per second per tunnel with certain configurations, though this performance depends heavily on internet quality, encryption overhead, and routing efficiency. While VPN isn't suitable for high-bandwidth production workloads, it serves important purposes: development and testing environments, disaster recovery standby connections, temporary connectivity needs, and hybrid deployments where interconnect handles primary traffic while VPN provides backup connectivity. The performance variability of VPN, due to its reliance on the public internet, makes it unsuitable for latency-sensitive or high-throughput production applications, but its simplicity and low cost make it valuable for specific use cases. Interconnect deployment process. Deploying Google Cloud Interconnect involves a carefully orchestrated sequence of steps spanning planning, physical implementation, configuration, and validation. Understanding this process is essential for project planning, resource allocation, and setting realistic timelines. The deployment process differs between Dedicated and Partner Interconnect, though they share common elements in planning and configuration phases. This workflow represents the typical journey from initial decision through production operation. The process begins with the planning phase, which is often underestimated in terms of importance and time required. Planning involves assessing your current network architecture, identifying which applications and workloads will use the interconnect connection, determining bandwidth requirements both for initial deployment and future growth, and evaluating whether Dedicated or Partner Interconnect better fits your needs. During planning, you'll also identify your technical resources, budget constraints, and timeline requirements. For Dedicated Interconnect, this phase includes determining if you have presence in a supported colocation facility or if you need to establish one. For Partner Interconnect, it involves selecting a service provider and understanding their specific requirements and timelines. Following planning comes the ordering phase, where you formally request the interconnect service. For Dedicated Interconnect, this means working through Google Cloud Console to create an interconnect attachment, specifying the colocation facility, selecting your bandwidth tier, and providing technical details like your desired VLAN IDs. Google will provide you with a letter of authorization, commonly called an LOA-CFA, which is a document authorizing the colocation facility to establish the physical connection between your equipment and Google's equipment. You take this LOA to the colocation facility, which will assign the cross-connect work to their technicians. For Partner Interconnect, ordering involves working with your chosen service provider to request the connection, specifying bandwidth requirements, and providing Google Cloud project details. The provider will handle much of the complexity, though you'll still need to coordinate with them. The diagram illustrates this complete deployment workflow as a sequence of steps flowing from top to bottom. The first step, planning and assessment, shows the decision point where you evaluate your requirements. This includes analyzing bandwidth needs by measuring current data transfers, projecting future growth, and adding headroom for unexpected spikes. You determine whether dedicated interconnect makes sense given your colocation situation and bandwidth needs, or whether partner interconnect's flexibility is more appropriate. This step also involves identifying which Google Cloud regions you'll connect to, as this affects latency, redundancy, and configuration options. The second step, order interconnect, splits into two paths depending on your choice. For dedicated interconnect shown on the left branch, you create the interconnect attachment in Google Cloud, specifying all technical parameters. Google generates the LOA-CFA document, which you download and provide to your colocation facility. The facility reviews the LOA, assigns technicians to install the cross-connect, and schedules the physical work. This can take days to weeks depending on the facility's workload and complexity of the cross-connect. For partner interconnect shown on the right branch, you contact your service provider with your requirements. The provider checks availability in their network, confirms they can deliver to your location, and initiates their internal ordering process. They coordinate with Google to establish the partner interconnect link on your behalf. Step 3. Physical connection represents the physical infrastructure work. For dedicated interconnect, colocation facility technicians install fiber optic cables from your equipment's cage or rack to Google's equipment location within the facility. They terminate the fibers properly, test for signal quality, and document the installation. You or your colocation provider may need to install the optical transceivers in your equipment. For partner interconnect, this step is mostly invisible to you. The service provider handles any necessary physical work to extend connectivity from their network to your location, whether that's installing new circuits or provisioning capacity on existing ones. The fourth step, configure border gateway protocol, involves setting up border gateway protocol to exchange routing information between your network and Google's network. For dedicated interconnect, you configure border gateway protocol directly on your edge routers, establishing a border gateway protocol session with Google's routers using the IP addresses Google provides. You'll advertise your on-premises IP ranges to Google and receive Google's routes in return. For partner interconnect, you configure border gateway protocol with your service provider's equipment, and the provider manages the border gateway protocol relationship with Google. In both cases, proper border gateway protocol configuration is critical. Mistakes can cause routing issues, black hole traffic, or create security vulnerabilities. Step 5. Test connection is crucial before declaring the interconnect production ready. You start with basic Layer 1 and Layer 2 tests, verifying that the physical connection is up and that VLAN tagging works correctly. Then you move to Layer 3 testing, confirming that IP routing works and that you can reach Google Cloud resources. You should test both directions, from on-premises to cloud and from cloud to on-premises. Performance testing validates that you are achieving expected bandwidth and latency. Failover testing, if you have redundant connections, ensures that traffic correctly fails over to backup paths when primary paths fail. The final step, go live, represents the transition to production use. You migrate production traffic from existing connectivity, whether that's VPN connections or internet-based access, to the new interconnect connection. This migration is typically done gradually, starting with non-critical workloads to gain confidence, then moving increasingly important applications. You establish monitoring and alerting to detect issues quickly, document the configuration for your operations team, and train staff on the new infrastructure. Going live isn't a single moment but rather a process that unfolds over days or weeks as you gain confidence and move more workloads to the dedicated connection. Interconnect use cases. Understanding the practical use cases for Google Cloud Interconnect helps you identify whether it's the right solution for your organization's specific needs. While the technical specifications and bandwidth numbers are important, the real value becomes clear when you examine how organizations actually use these connections to solve business problems. The use cases span different industries, workload types, and architectural patterns, each benefiting from the dedicated private connectivity that Interconnect provides. Hybrid cloud architectures represent one of the most common use cases for Interconnect. In a hybrid architecture, you maintain some workloads on premises while moving others to the cloud, with tight integration between both environments. This pattern is prevalent in organizations undergoing digital transformation who can't migrate everything to the cloud simultaneously due to technical, regulatory, or business constraints. Interconnect allows these hybrid architectures to function smoothly by providing low latency, high bandwidth connectivity between environments. Applications can span both on-premises and cloud, with front-end web tiers in the cloud leveraging on-premises databases, or cloud-based analytics platforms processing data stored in on-premises systems. The key requirement is that these cross-environment interactions must perform well, and public internet connectivity typically doesn't meet the latency and consistency requirements. Enterprise application migration is another major use case that heavily relies on Interconnect. When large organizations decide to move applications to Google CP, they rarely do a complete lift and shift in one go. Instead, they migrate application tiers progressively over weeks or months. During this migration period, parts of the application run on premises while other parts run in the cloud, requiring constant communication between environments. Interconnect provides the stable, high-performance connectivity needed during these migration phases. It also serves as the data transfer mechanism for moving large datasets, virtual machine images, and backup archives to the cloud. Without Interconnect, these transfers over internet connections would take prohibitively long and risk timeouts or failures. The diagram shows 4 primary use cases arranged in a grid, each with specific requirements and benefits. The top left quadrant covers hybrid cloud workloads, which need seamless integration between on-premises and cloud environments. The architecture might involve databases remaining on-premises due to licensing or compliance requirements while application tiers move to the cloud for scalability. Or you might have specialized hardware on-premises for specific processing tasks, with cloud resources handling everything else. The low latency of Interconnect makes these split architectures viable. Applications don't experience the delays and jitter that would occur over internet connections. The bandwidth supports the constant data exchange these hybrid applications require. The top right quadrant details large-scale data transfer requirements. Organizations with massive datasets need reliable, fast ways to move data to Google Cloud. For example, media companies transferring petabytes of video files for cloud-based rendering and processing, scientific research organizations uploading enormous datasets for analysis, financial institutions moving transaction histories for compliance archiving, and healthcare providers migrating medical imaging archives. Attempting these transfers over internet connections would take weeks or months and face reliability issues. With Interconnect, particularly high-bandwidth dedicated interconnect, you can move terabytes per hour, making even massive migrations feasible. The consistent performance means you can schedule and predict transfer completion times accurately. The bottom left quadrant addresses disaster recovery and backup scenarios. Many organizations use Google Cloud as their disaster recovery target, replicating critical systems and data to the cloud so they can fail over if their primary data center experiences an outage. Disaster recovery requires continuous replication of data, which generates substantial network traffic. Interconnect provides the bandwidth for this ongoing replication while keeping costs predictable, as you're not paying for internet data transfer. The low latency ensures that replication stays current. Even real-time replication with synchronous writes to the cloud becomes feasible with Interconnect's single-digit millisecond latencies. During an actual disaster, when you need to fail over operations to the cloud, Interconnect ensures that users and applications can access the cloud-based systems with performance similar to what they experienced with on-premises systems. The bottom right quadrant covers branch office connectivity, particularly relevant for Partner Interconnect with its flexible bandwidth options. Organizations with many branch offices can use Partner Interconnect to give each location private, secure access to cloud applications and resources. Instead of each branch accessing cloud resources over the public internet, they connect through Partner Interconnect, improving security, reliability, and performance. A retail chain might use this to connect hundreds of stores to cloud-based point-of-sale systems, inventory management, and analytics platforms. A professional services firm might use it to give regional offices access to cloud-based file storage, customer relationship management systems, and collaboration tools. The granular bandwidth options mean you can right-size each location's connection based on the number of users and applications, avoiding over-provisioning while ensuring good user experience. Interconnect cost considerations. Understanding the cost structure of Google Cloud Interconnect is essential for budgeting, comparing alternatives, and optimizing your cloud network spending. The costs involve both one-time expenses and recurring monthly charges, and they vary significantly between Dedicated and Partner Interconnect. Beyond the obvious connectivity charges, there are several other cost factors that affect the total cost of ownership. Making informed decisions requires looking at the complete picture of costs, not just the headline connection fees. The cost structure for interconnect has several components. First, there are the interconnect port charges, which are monthly fees Google charges for the connection itself. These vary by bandwidth tier and connection type. Second, if you're using Dedicated Interconnect, you'll have colocation costs for the rack space, power, and remote hand services at the facility where you establish your connection. Third, you'll have the cost of your networking equipment, including routers, switches, and optical transceivers. Fourth, there are data egress charges for traffic leaving Google Cloud through the interconnect connection, though these are typically lower than internet egress charges. Finally, if you're using Partner Interconnect, your service provider will charge their own fees for the connection to their network and for the Partner Interconnect service itself. Dedicated Interconnect's cost model is relatively straightforward but involves larger numbers. The Google port charge for a 10 gigabits per second interconnect connection is roughly $1,650 per month per connection. For a 100 gigabits per second connection, it's approximately $14,000 per month. These prices vary slightly by region and are subject to change, but they provide a baseline for planning. Remember that Google recommends redundant connections, so you're typically provisioning 2 connections for production workloads, doubling these costs. On top of Google's charges, you'll pay colocation costs. These vary widely by facility and market but typically run several hundred to several $1,000s per month depending on how much rack space you need, the power draw of your equipment, and the services you require from the facility. Looking at the cost comparison table, we see the breakdown across different aspects. The connection port fee column shows what Google charges monthly for each bandwidth tier. Dedicated Interconnect shows higher absolute numbers but offers more bandwidth per dollar. Partner Interconnect's fees are lower for smaller bandwidths, making it cost-effective for organizations that don't need massive capacity. The fees roughly scale with bandwidth, though not linearly. Higher bandwidth tiers generally offer better per megabit economics. The colocation costs column reveals a key differentiator between Dedicated and Partner Interconnect. For Dedicated Interconnect, you pay colocation facility charges that might include monthly rack rental ranging from $500 to $3,000 depending on the facility and market. Power charges often billed per kilowatt at rates varying from $150 to $300 per kilowatt per month. Remote hand services for when facility technicians need to perform work on your behalf, and potentially cross-connect fees for the physical fiber between your equipment and Google's. These costs add up quickly and often surprise organizations new to colocation. For Partner Interconnect, colocation costs are zero from your perspective because you're not establishing presence in Google's colocation facilities. Your service provider absorbs these costs as part of their business model. The equipment costs column addresses the networking hardware required. For Dedicated Interconnect, you need routers capable of 10 or 100 gigabit interfaces, which are expensive devices. An enterprise router with the necessary ports, processing power, and features might cost anywhere from $20,000 to well over $100,000 depending on the model and capabilities. You'll need optical transceivers for the fiber connections, which run from $500 to several $1,000s each. If you're implementing redundancy across multiple routers, these equipment costs multiply. For partner interconnect, your equipment requirements are often less demanding because you're connecting to your service provider at whatever speed you've negotiated, which might be 1 gigabit Ethernet or another standard speed that your existing equipment already supports. Many organizations find they can use their current edge routers for partner interconnect, eliminating or reducing equipment upgrade costs. The data egress rates column shows per gigabyte charges for traffic leaving Google CP through your interconnect connection. Google charges for egress traffic, but interconnect egress rates are significantly lower than internet egress rates. Typical interconnect egress charges might be around 2 to 5 cents per gigabyte depending on region and volume, compared to 8 to 12 cents per gigabyte for internet egress. For organizations transferring large amounts of data from Google CP to on-premises systems regularly, this difference can represent substantial monthly savings that help offset the connection costs. If you're moving terabytes of data monthly, the egress savings alone might justify interconnect from a pure cost perspective, even without considering the performance benefits. The additional considerations column captures other factors affecting total cost. For dedicated interconnect, you might need to hire or train staff with the expertise to manage border gateway protocol, troubleshoot layer 1 issues, and coordinate with colocation facilities. These ongoing operational costs can be significant. You're also responsible for monitoring and maintaining your equipment in the colocation facility. For partner interconnect, you pay your service providers monthly fees for their service, which typically bundle the provider's network access, the partner interconnect service itself, and support. These fees vary widely by provider, location, and bandwidth tier. You also have less control over some cost elements. If the provider raises their prices, you have limited options beyond switching providers, which introduces transition costs and risks. Choosing between dedicated and partner interconnect. The decision between dedicated interconnect and partner interconnect is one of the most important architectural choices you'll make when planning your Google Cloud network connectivity. While both options provide private, dedicated connectivity to Google Cloud, they differ significantly in terms of bandwidth options, location requirements, costs, operational complexity, and control. Making the right choice requires carefully weighing your specific requirements against the characteristics of each option. There's no universally correct answer. The right choice depends entirely on your organization's unique situation. Several key factors should guide your decision-making process. First, consider your bandwidth requirements both for initial deployment and future growth. If you need 10 gigabits per second or more right from the start, or if you anticipate growing to that level within a year or two, dedicated interconnect might be the better choice. Its cost per megabit is lower at these higher bandwidths. However, if your needs are under 10 gigabits, especially if they're under 1 gigabit, partner interconnect's granular tiers probably offer better economics. Second, evaluate your geographic situation. Do you have equipment in or near a Google-supported colocation facility? If not, are you willing to establish a presence there? If the answer is no to both questions, partner interconnect is likely your only practical option. Third, consider your operational preferences and capabilities. Some organizations prefer the control that comes with managing their own infrastructure end-to-end, even with the added complexity. Others prefer to leverage service provider expertise and offload operational burden, even if it means less direct control. The decision matrix in the diagram provides a structured way to evaluate your situation. The left column lists critical decision factors, while the middle and right columns show how dedicated and partner interconnect address each factor. Starting from the top, bandwidth requirements shows that dedicated interconnect is optimal when you need 10 gigabits per second or higher. The economies of scale at these bandwidths make dedicated interconnect cost competitive despite its higher ancillary costs. Partner Interconnect is marked as optimal for requirements under 10 gigabits per second, where its flexible tiers allow you to match your purchase to your needs without over-provisioning. The critical bandwidth is 10 gigabits. Above that, lean toward dedicated. Below that, lean toward partner. Geographic location requirements reveal a fundamental difference. Dedicated Interconnect requires equipment in Google-supported colocation facilities. There are only a limited number of these facilities globally, concentrated in major metropolitan areas with strong internet exchange presence. If your primary data center or facilities aren't in or near these locations, Dedicated Interconnect requires relocating equipment or establishing new infrastructure, which might not be feasible. Partner Interconnect, in contrast, is available anywhere your service provider operates. Since major carriers and service providers have much broader geographic reach than Google's colocation points, Partner Interconnect dramatically expands the locations from which you can establish private Google Cloud connectivity. Setup complexity differences are significant. Dedicated Interconnect is marked high complexity because you're responsible for everything. Coordinating with the colocation facility, managing the LOA-CFA process, configuring routers including BGP, installing and managing equipment, and troubleshooting any issues across all these layers. This complexity requires skilled staff and can lead to longer deployment times. Partner Interconnect shows medium complexity because your service provider handles much of the infrastructure work. You still need to configure your connectivity to the provider and coordinate the Partner Interconnect attachment creation, but the physical and Google-facing configuration is abstracted away. This reduced complexity often means faster deployments and less specialized expertise required from your team. Initial cost considerations show stark differences. Dedicated Interconnect has high initial costs encompassing colocation setup fees, which might include installation charges, first month's rent, and security deposits, equipment purchases for high-end routers and transceivers potentially totaling $50,000 to $150,000 or more, and the time investment for planning and coordination. Partner Interconnect has lower initial costs because you're typically using existing equipment or making modest upgrades, avoiding colocation setup, and leveraging the provider's existing infrastructure. For many organizations, especially small and medium businesses, this difference in initial investment is decisive. Ongoing operational costs present a more nuanced picture. Dedicated Interconnect shows Google port fees plus colocation expenses plus equipment maintenance, but you have direct control over these costs once established. Partner Interconnect shows Google port fees plus service provider fees, which might be higher than your colocation costs would be, but you're not responsible for equipment maintenance or facility management. The total ongoing cost depends heavily on your specific service provider and their pricing model. Control and flexibility shows that Dedicated Interconnect provides full control over your network stack, the ability to implement specific configurations, and flexibility to modify your setup as needed. Partner Interconnect provides less control because you're dependent on your service provider's capabilities, configurations, and policies, but many organizations view this as an acceptable trade-off for reduced operational burden. The recommendation section at the bottom provides clear guidance. Choose Dedicated Interconnect when you need 10 gigabits per second or higher bandwidth, already have or can easily establish colocation presence, have the technical expertise to manage complex networking infrastructure, want maximum control over your network configuration, and can absorb the higher initial costs. Choose Partner Interconnect when your bandwidth needs are under 10 gigabits per second, you lack proximity to Google colocation facilities, you prefer to leverage service provider expertise and support, you want lower initial costs and faster deployment, or you have multiple smaller sites that need connectivity with granular bandwidth requirements. Many organizations end up using both. Dedicated Interconnect for their primary data centers with high bandwidth needs, and Partner Interconnect for branch offices, disaster recovery sites, and smaller locations. VLAN attachments explained. VLAN attachments are a fundamental concept in Google Cloud Interconnect that enable you to logically separate different types of traffic across your physical interconnect connection. Understanding VLAN attachments is crucial because they determine how your on-premises networks connect to specific virtual private cloud networks in Google Cloud. Rather than requiring separate physical connections for each VPC or network segment you want to reach, VLAN attachments allow you to multiplex multiple logical connections over a single physical interconnect link using standard 802.1x VLAN tagging. Think of your physical interconnect connection as a highway with multiple LANs. Each VLAN attachment represents a dedicated LAN for specific traffic, ensuring isolation between different workloads, environments, or business units. For example, you might create separate VLAN attachments for production traffic, development and testing traffic, and disaster recovery replication traffic, all traveling over the same physical connection but remaining logically isolated from each other. This approach maximizes the utilization of your expensive interconnect bandwidth while maintaining the security and separation boundaries your organization requires. The architecture diagram shows how VLAN attachments create this logical separation. At the bottom, we have the physical interconnect connection, which is your actual 10 gigabit or 100 gigabit fiber link between your equipment and Google's network. This physical connection carries all traffic but uses VLAN tags to separate different flows. Above the physical layer, we see 3 VLAN attachments represented, each with a unique VLAN ID. VLAN 1001 is shown connecting to production VPC in the US Central 1 region. This attachment carries all traffic destined for your production workloads running in that specific VPC and region. VLAN 1002 connects to development VPC, also in US Central 1. This separation ensures that development traffic, which might include large code deployments, database refreshes from production snapshots, or experimental configurations, doesn't interfere with production traffic even though both travel over the same physical wire. The third VLAN attachment, using VLAN ID 1003, connects to production VPC but in a different region, US East 1. This demonstrates another important use case. The same physical interconnect connection can provide access to multiple Google Cloud regions simultaneously. You don't need separate physical connections to reach different regions. You simply create additional VLAN attachments. Each VLAN attachment has several important properties. It has a unique VLAN ID between 1 and 4094, which must match on both your router configuration and Google's configuration. It has cloud router associations, which handle the BGP routing for that specific attachment. Each VLAN attachment can advertise different routes to your on-premises network, allowing fine-grained control over which cloud resources are reachable through which attachment. The attachment also defines bandwidth allocation, though this is typically informational rather than enforced, as all attachments share the physical connection's total bandwidth. Finally, each VLAN attachment connects to exactly one VPC in one region, though a single VPC can have multiple VLAN attachments for redundancy or to connect from multiple physical interconnect locations. Creating VLAN attachments in Google Cloud. Creating VLAN attachments involves using the G-Cloud command line tool or the Google Cloud Console to define the logical connection between your interconnect and a specific VPC. The process requires understanding several parameters that control how the attachment functions and integrates with your network architecture. While the actual creation command is straightforward, proper planning of these parameters is critical to ensure the attachment works correctly and aligns with your routing and security policies. The G-Cloud command shown creates a VLAN attachment with specific configuration parameters. Let's walk through each parameter to understand its purpose and impact. The command starts with G-Cloud Compute Interconnects Attachments Create, which is the base command for creating any type of interconnect attachment. The name Production Attachment 1 is the identifier you'll use to reference this attachment in future commands and in the Google Cloud Console. Choosing descriptive names is important, especially in large deployments with many attachments. Common naming patterns include the environment, VPC name, region, and a sequence number. The region parameter specifies US Central 1, which is the Google Cloud region where this VLAN attachment will terminate. This must match the region where your target VPC and cloud router reside. You cannot create a VLAN attachment that connects to resources in multiple regions. Each attachment is region-specific. The router parameter specifies production router 1, which is the cloud router that will handle BGP routing for this attachment. The cloud router must already exist in the same region and be associated with the VPC you want to connect to. The router manages route advertisements between your on-premises network and Google Cloud, dynamically updating as your cloud infrastructure changes. The interconnect parameter identifies the physical interconnect connection this VLAN attachment will use. In this example, it's US Central 1 Interconnect 1, which should be the name of your dedicated interconnect or partner interconnect connection. One physical interconnect can support multiple VLAN attachments, up to the VLAN limits of your equipment. The VLAN parameter specifies the VLAN ID, here set to 1001. This is the 802.1x VLAN tag that will be used to separate this attachment's traffic from other VLAN attachments on the same physical link. You must configure the matching VLAN ID on your on-premises router. VLAN IDs must be unique across all attachments using the same physical interconnect. The MTU parameter sets the maximum transmission unit to 1500 bytes, which is the standard Ethernet frame size. Google Cloud Interconnect also supports jumbo frames with MTU up to 1460 for certain configurations, which can improve performance for large data transfers by reducing packet overhead. However, jumbo frames require support across your entire LAN path, including your routers, switches, and any intermediate devices. The bandwidth parameter specifies the intended bandwidth for this attachment. This is informational and used for monitoring and capacity planning. It doesn't enforce a hard limit. The value of 2 gigabits per second in this example means you're planning for this attachment to carry up to 2 gigabits per second of traffic, helping you track utilization and plan upgrades. The output section shows what Google CP returns after successful creation. The VLAN attachment receives a unique ID, here attachment-ABC123DEF456, which is Google's internal identifier. The state shows pending partner initially because additional configuration steps are required before the attachment becomes active. For dedicated interconnect, you must configure the matching VLAN on your router. For partner interconnect, you must work with your service provider to activate the attachment on their side. The cloud router assignment confirms which router will handle this attachment's routing. The VLAN ID is confirmed as 1001, and the attachment is shown associated with the specified interconnect connection and region. This information is crucial for the next steps of configuring your on-premises equipment to complete the connection. BGP Configuration Fundamentals. Border Gateway Protocol, or BGP, is the routing protocol that makes cloud interconnect dynamic and scalable. Unlike static routing where you manually configure every route on both sides of the connection, BGP allows routers to automatically exchange routing information and adapt to network changes. In the context of cloud interconnect, BGP runs between your on-premises routers and Google's cloud router, enabling automatic route propagation as you add or remove resources in Google Cloud or change your on-premises network topology. BGP's importance in cloud interconnect cannot be overstated. It's what allows your on-premises applications to automatically discover new IP ranges when you create new subnets in your VPC. It enables automatic failover when you have redundant interconnect connections. If one connection fails, BGP withdraws those routes and traffic automatically shifts to the surviving connection. BGP also allows sophisticated traffic engineering, where you can influence which interconnect connection carries which traffic through careful manipulation of BGP attributes like AS path prepending, local preference, and communities. The configuration example shows a typical BGP setup on your on-premises router for connecting to Google Cloud. Let's examine each section and understand why these settings matter. The first section configures the BGP router process with router BGP 65001. The number 65001 is your Autonomous System Number or ASN. An ASN uniquely identifies your network in the global BGP routing system. For private connections like interconnect, you typically use a private ASN in the range 64512 to 65534, or the extended range for 32-bit ASNs. Google will provide you with the ASN they're using, and you configure your own ASN, which must be different from Google's. The Neighbor Configuration section establishes the BGP peering relationship with Google's cloud router. The command neighbor 169.254.1.1 specifies the IP address of Google's BGP endpoint. Google uses linked local IP addresses in the 169.254.0.0/16 range for BGP peering, which are special IP addresses used only for the direct connection between routers. These addresses don't need to be raw table on your broader network. They exist only on the interconnect link itself. The remote as 16550 parameter specifies Google's ASN. Google uses ASN 16550 for most cloud router configurations, though this can vary in some situations. The remote as identifies which autonomous system you're peering with, and it must match what Google has configured on their side. The update source VLAN 1001 parameter is crucial. It tells your router which interface to use as the source for border gateway protocol packets. This must be the VLAN interface you created for this interconnect attachment. The next hop self-configuration affects how your router advertises routes to the rest of your network. When your border gateway protocol router learns routes from Google and redistributes them to your internal network, it sets itself as the next hop, ensuring that other routers in your network know to send Google Cloud-bound traffic through this border gateway protocol router. Without this setting, your internal routers might receive routes with Google's address as the next hop, which they can't reach directly. The network statements advertise your on-premises IP ranges to Google Cloud. The network 10.0.0.0 mask 255.255.255.0 line tells BGP to advertise your 10.0.0.0/24 subnet to Google. Any packets in Google Cloud destined for this range will be sent through the interconnect connection to your network. You repeat this command for each subnet you want to make reachable from Google Cloud. The final section address family IPv4 and network commands can be used for IPv4 specific configurations, though the syntax varies by router vendor. This structure ensures that both IPv4 routes are properly exchanged. Once BGP is configured and established, you can verify the session status with commands like show IPBGP summary to see if the neighbor relationship is established and routes are being exchanged. BGP session states and troubleshooting. Understanding BGP session states is essential for diagnosing interconnect connectivity issues. BGP sessions progress through several states as they establish, and recognizing these states helps you identify exactly where a problem exists. When troubleshooting interconnect, the BGP session state is often your first diagnostic indicator, telling you whether the issue is physical connectivity, configuration mismatch, or something else entirely. BGP sessions begin in the idle state, which is the initial state when BGP is first configured or after a session has been reset. In idle, the router is not actively trying to establish a BGP connection. It's waiting for an administrative trigger or timer to begin the connection attempt. If a session remains in idle, it usually indicates that BGP isn't enabled on the interface, there's an administrative shutdown on the neighbor configuration, or there's a fundamental configuration error preventing the session from starting. From idle, once the router decides to initiate BGP, it transitions to connect state where it attempts to complete a TCP handshake with the BGP neighbor. BGP runs over TCP port 179, so firewalls and access control lists must permit this traffic. The diagram illustrates the complete BGP session state machine as a flow from top to bottom. At the top, we see the idle state, where the session starts or returns after errors. The characteristics listed include no active connection attempt, waiting for start event, and requires manual or timer trigger. This state is normal during initial configuration or immediately after explicitly resetting a BGP session. An arrow points down to connect state, representing the transition when the router begins connection establishment. Connect state shows active TCP connection attempt, waiting for TCP handshake to complete, and timeout causes return to idle. If the TCP connection succeeds, BGP moves to the next state. If it fails, the session may cycle between idle and connect until it succeeds or is fixed. The active state appears next in the flow. Despite its name suggesting normal operation, active is actually a troubleshooting state indicating problems. The characteristics show TCP connection failed, attempting to restart connection, and indicates configuration or connectivity issue. If you see a BGP session stuck in active state, it typically means your router can't read the neighbor's IP address, there's a firewall blocking TCP port 179, or there's a configuration mismatch preventing the TCP connection from completing. Active state often cycles with connect as the router repeatedly tries and fails to establish the connection. Once the TCP connection succeeds, BGP moves to open sent state, shown next in the flow. This state indicates that sent BGP open message, waiting for open reply from neighbor, and negotiating BGP version and capabilities. The open message contains important information like the ASN of each router, the router ID, and optional capabilities like route refresh or multi-protocol extensions. If the neighbor accepts the open message and sends its own, the session advances. If there's an ASN mismatch or other incompatibility, the session will reset back to idle with an error notification. Open confirm state follows successful open exchange. The characteristics show received and accepted open message, waiting for keep alive or notification, and almost established but not fully operational. This is typically a very brief state as routers exchange keep alive messages to confirm the session is stable. From open confirm, the session finally reaches established state at the bottom of the diagram. This is the goal. The session is fully operational and exchanging routes, peers sending and receiving updates, and this is the healthy normal state. In established state, routers exchange routing information and keep the session alive with periodic keep alive messages. This is where your BGP session should spend almost all its time during normal operation. When troubleshooting, you use commands like show IP BGP summary on Cisco routers or show BGP summary on Juniper devices to see the current state of each BGP neighbor. If your Google Cloud Interconnect BGP session isn't in established state, the specific state it's stuck in gives you valuable clues. Idle or connect suggests physical or reachability problems. Active indicates ongoing connection failures. Open sent or open confirm point to configuration mismatches like incorrect ASN values. Understanding this state progression allows you to quickly narrow down where the issue lies and focus your troubleshooting efforts appropriately. Redundancy architecture for high availability. High availability is critical for production workloads relying on cloud interconnect. A single interconnect connection, no matter how reliable, represents a single point of failure that can bring down your entire hybrid cloud architecture if it fails. Google strongly recommends, and most enterprises require, implementing redundant interconnect connections that protect against failures at multiple levels. Individual connection failures, equipment failures, facility-level outages, and even regional disasters. Understanding and implementing proper redundancy architecture is essential for meeting enterprise service-level agreements and ensuring business continuity. The foundation of interconnect redundancy involves provisioning at least two separate interconnect connections. But redundancy isn't just about having two connections. It's about ensuring those connections don't share failure domains. If both connections run through the same router, that router becomes a single point of failure. If both connections terminate in the same colocation facility, a facility outage affects both. If both connections use the same fiber path, a single fiber cut disrupts both. True redundancy requires diversity at every level. Different routers, different colocation facilities, different fiber paths, and ideally different geographic regions. The architecture diagram illustrates a comprehensive redundancy design that protects against multiple failure scenarios. Starting at the bottom left, we have your on-premises data center with two edge routers, Router A and Router B. These routers are physically separate devices, ideally from different vendors to protect against vendor-specific software bugs, installed in different racks to protect against power distribution failures, and connected to different network segments within your data center. This router redundancy ensures that failure of any single router doesn't disrupt connectivity. From Router A, a connection extends to Colocation Facility 1, shown in the diagram as one of two separate facilities. This might be an Equinix data center in one part of the city. Within Colocation Facility 1, Router A connects to Google Edge Router 1, which is Google's equipment dedicated to interconnect services. This represents your first dedicated interconnect connection, labeled Connection 1. The connection uses specific fiber paths installed by the colocation facility, typically using diverse routing through the building to avoid single conduit failures. Similarly, from Router B, a separate connection extends to Colocation Facility 2, which might be a different Equinix facility across town or a CoreSite facility in another area. Router B connects to Google Edge Router 2, establishing Connection 2. The diagram shows both Google Edge routers connecting to Google's global network, which is their private fiber backbone interconnecting all Google facilities worldwide. The redundancy continues here. Google's network is itself highly redundant with multiple paths between any 2 points. From Google's global network, connections extend to your Google Cloud VPCs. The diagram shows connections to VPCA in US Central 1 and VPCB in US East 1, demonstrating that your redundant interconnect connections can provide access to multiple VPCs across multiple regions simultaneously. The key aspects of this redundancy architecture are highlighted in boxes throughout the diagram. Diverse physical paths indicates that Connection 1 and Connection 2 must not share fiber routes. If both connections use the same fiber bundle through the streets, a construction accident cutting that fiber would disrupt both connections simultaneously. You should work with the colocation facilities to document and verify the fiber paths, ensuring they take different routes from your data center through the city to the respective facilities. Different colocation facilities provides facility-level redundancy. If colocation facility 1 experiences a power outage, fire, flooding, or other disaster, colocation facility 2 remains operational, keeping at least one interconnect connection active. Separate edge routers ensures that both your on-premises routers and Google's edge routers are independent. This protects against hardware failures, software bugs, or maintenance activities that might require taking a router offline. Border Gateway Protocol automatic failover is the mechanism that makes this redundancy automatic and seamless. Both routers advertise the same routes via Border Gateway Protocol, but you can influence which path is preferred using Border Gateway Protocol attributes. If the preferred connection fails, Border Gateway Protocol automatically converges to use the remaining connection within seconds to tens of seconds, depending on your Border Gateway Protocol timer settings. Applications might experience brief disruption during failover, but the connectivity automatically restores without manual intervention. Monitoring interconnect health and performance. Effective monitoring is crucial for maintaining reliable interconnect connectivity. Without proper monitoring, you might not know about problems until users complain about performance or connectivity issues. Proactive monitoring allows you to identify and address issues before they impact production workloads, plan capacity upgrades before hitting bandwidth limits, and maintain historical metrics for capacity planning and troubleshooting. Google Cloud provides comprehensive monitoring capabilities through Cloud Monitoring, formerly known as Stackdriver, with specific metrics for interconnect connections. The monitoring strategy for interconnect should cover multiple dimensions: connection availability to detect outages, bandwidth utilization to identify capacity constraints, error rates to catch degrading hardware or configuration issues, and BGP session health to ensure routing is functioning correctly. You should establish baseline performance metrics during normal operation, set thresholds that trigger alarms before problems become critical, and create dashboards that provide at-a-glance health visibility for operations teams. Many organizations integrate these metrics into their broader network monitoring platforms using APIs or exporters. Looking at the comprehensive monitoring dashboard diagram, we see 4 primary metric categories arranged in quadrants. The top left quadrant shows connection status metrics, which are your most critical indicators of interconnect health. The metrics include link state showing open or down status, which indicates whether the physical connection is active. If this shows down, you have a Layer 1 or Layer 2 problem requiring immediate attention. BGP session state should show established during normal operation. If it shows anything else like active, open sent, or idle, you have a BGP configuration issue or connectivity problem preventing route exchange. Packet loss percentage is another connection status metric that reveals physical layer problems. In a healthy interconnect connection, packet loss should be 0 or very close to 0, typically less than 0.01%. If you see consistent packet loss above this threshold, it suggests bad optics, misconfigured interfaces, or problems in the physical infrastructure. Error count tracks various error types including CRC errors, which indicate physical layer problems like bad cables or transceivers, frame errors suggesting misconfiguration of frame size or encapsulation, and input errors, which are a catch-all for various receive problems. These error counts should remain at 0 or increase very slowly over time. Rapidly increasing errors indicate immediate problems requiring investigation. The top right quadrant displays bandwidth utilization metrics, essential for capacity planning and performance optimization. Ingress traffic measures data flowing from your on-premises network into Google Cloud. This might represent application data being uploaded, backup data being archived to cloud storage, or database replication traffic. Tracking ingress utilization helps you understand whether you're approaching your connection's capacity. If you consistently hit 70 to 80% of your available bandwidth, it's time to plan for an upgrade. Egress traffic measures data flowing from Google Cloud back to your on-premises network, such as query results from cloud databases, files retrieved from cloud storage, or video streams from cloud-based media processing. The peak usage metric tracks your highest bandwidth consumption, typically sampled at 1-minute or 5-minute intervals. This reveals usage patterns and helps identify traffic spikes that might cause temporary performance degradation even if average utilization is low. Average utilization over longer periods like hours or days provides the big picture of your capacity usage trends. If average utilization is steadily climbing, you need to plan capacity upgrades. The combination of peak and average metrics tells you whether you have occasional spikes requiring traffic engineering or sustained high usage requiring more bandwidth. The bottom left quadrant covers latency metrics, which measure the time it takes for packets to traverse the interconnect connection. Round-trip time, or RTT, measures the time for a packet to travel from your on-premises network to Google Cloud and back. For interconnect connections, you typically expect RTT under 10 milliseconds for same metro connections, and under 50 milliseconds for cross-country connections. If RTT suddenly increases, it might indicate routing issues, congestion, or problems in Google's network. Jitter measures variation in latency. High jitter appears as inconsistent response times and can severely impact real-time applications like voice over IP or video conferencing. Interconnect connections should exhibit very low jitter, typically under 5 milliseconds. Packet delay variation is related to jitter, but measured differently, showing how much consecutive packets vary in their arrival time. High packet delay variation suggests congestion or buffering issues somewhere in the path. One-way delay is harder to measure than RTT because it requires time synchronization between source and destination, but it can reveal asymmetric routing problems where traffic takes different paths in each direction with different performance characteristics. The bottom right quadrant shows alert configuration, which transforms metrics into actionable notifications. You should create alarms for critical thresholds like link down, BGP session not established, or packet loss above 0.1%. These require immediate response. Warning thresholds should alert for situations that are not immediate failures but need attention, such as bandwidth utilization above 70%, error rates increasing steadily, or latency above expected baselines. Capacity planning alerts trigger when utilization trends suggest you will hit capacity within a defined timeframe, giving you advance notice to plan upgrades. Historical trends should be reviewed periodically to identify slow degradation, seasonal patterns, or gradual capacity consumption that might not trigger immediate alarms but needs long-term planning. Effective alerting balances being informed about problems versus being overwhelmed with noise. Start conservative and tune thresholds based on your environment's normal behavior. Security considerations for interconnect. Security is a critical consideration when implementing Cloud Interconnect, even though the connections are private and don't traverse the public internet. While interconnect provides physical isolation from internet traffic, it creates a direct path between your on-premises network and Google Cloud, which requires careful security architecture to prevent unauthorized access, contain breaches, and maintain compliance with regulatory requirements. The security approach for interconnect differs significantly from internet-based connectivity and requires specific considerations around network segmentation, access control, traffic filtering, and monitoring. The fundamental security principle for interconnect is defense in depth, meaning you implement security controls at multiple layers rather than relying on a single protection mechanism. While the physical isolation of interconnect provides one security layer, you must also implement logical controls including firewall rules to restrict which traffic can traverse the interconnect, network segmentation to isolate different types of workloads, identity and access management to control who can modify interconnect configurations, encryption for sensitive data even on private connections, and comprehensive logging to detect and investigate security incidents. Each of these layers provides partial protection, but together they create a robust security posture. The security architecture diagram illustrates multiple security layers protecting interconnect connectivity. At the bottom, we see your on-premises data center with several security components. The edge firewall is your first line of defense, positioned between your internal network and the interconnect connection. This firewall should implement strict rules allowing only necessary traffic to traverse the interconnect. For example, you might allow specific application servers to reach specific Google Cloud subnets on specific ports, while blocking everything else. Many organizations implement a default deny policy where all traffic is blocked unless explicitly permitted, forcing careful consideration of each allowed flow. Next to the firewall, the diagram shows an IDS, which monitors traffic traversing the interconnect for malicious patterns. While interconnect traffic doesn't face the same internet threat landscape, an IDS can detect lateral movement by attackers who have compromised either your on-premises network or Google Cloud and are attempting to pivot between environments. The IDS might detect port scans, known malware signatures, or suspicious traffic patterns that indicate reconnaissance or exploitation attempts. The Network Access Control List, shown alongside the IDS, provides additional packet filtering, often implemented on routers or switches to enforce allowed protocols and ports at the network layer. The arrow from on-premises to Google Cloud passes through a section labeled Private Isolated Connection, emphasizing that interconnect traffic doesn't traverse the public internet. This isolation is a key security benefit, as your traffic isn't exposed to internet-based attacks, man-in-the-middle attempts, or the unpredictable routing of internet paths where traffic might traverse adversarial networks. However, Private doesn't mean secure by default. You must still implement the other security layers. Within Google Cloud, shown in the upper portion of the diagram, we see the VPC firewall rules component. Google Cloud implements stateful firewall rules at the VPC level, allowing you to control ingress and egress traffic for each virtual machine instance, subnet, or network tag. These firewall rules should mirror the defense in-depth approach used on-premises. Even though traffic is coming from your trusted on-premises network via interconnect, you should implement rules that allow only necessary communication. For example, web servers might accept HTTPS traffic from on-premises load balancers, but should block all other ports and protocols. Database servers might accept connections only from specific application server IP addresses, preventing unauthorized database access even if an attacker gains access to your Google Cloud environment. The Identity and Access Management component, shown as IAM, controls who can read, create, modify, or delete interconnect resources in Google Cloud. IAM is crucial because interconnect configurations determine network connectivity, and unauthorized changes could create security holes or disrupt service. You should implement least privilege access, granting interconnect management permissions only to network administrators who need them, requiring multi-factor authentication for accounts with interconnect permissions, and auditing all configuration changes. VPC service controls, shown in the diagram, provide an additional security layer for protecting sensitive data in Google Cloud services. Service controls let you define security perimeters around Google Cloud resources, restricting data exfiltration even if an attacker gains network access. For example, you might configure service controls to ensure that data in BigQuery can only be accessed from within the VPC or through the interconnect connection, preventing unauthorized access via the public internet even if firewall rules were misconfigured. The audit logging component, displayed at the top, records all activities related to your interconnect and VPC resources. These logs capture who made what changes when, all network flows that are allowed or denied by firewall rules, all BGP route advertisements and withdrawals, and all authentication and authorization decisions. These logs are invaluable for security incident investigation, compliance reporting, and troubleshooting. You should export these logs to a secure long-term storage location and integrate them with your security information and event management or SIM system for analysis and alerting. Interconnect and VPC peering integration. Understanding how Cloud Interconnect integrates with VPC network peering is important for complex architectures involving multiple VPCs and shared services. VPC network peering allows you to connect two VPC networks within Google Cloud, enabling resources in different VPCs to communicate using private IP addresses without traversing the public internet. When combined with interconnect, this creates powerful architectural patterns where your on-premises network can reach multiple VPCs through a single interconnect connection, or where shared service VPCs provide centralized resources accessible from both on-premises and multiple tenant VPCs. The interaction between interconnect and VPC peering has specific rules and limitations that architects must understand. By default, routes learned via interconnect in one VPC do not automatically propagate across VPC peering connections. This means if you establish an interconnect connection to VPC-A, and VPC-A is peered with VPC-B, resources in VPC-B cannot automatically read your on-premises network. This default behavior is intentional, preventing unintended route propagation and maintaining network isolation. However, Google Cloud provides a feature called Export and Import Custom Routes that allows you to control whether routes learned via interconnect should be shared across peering connections. The architecture diagram shows a common pattern called a hub and spoke or shared services topology. At the bottom, your on-premises data center connects via interconnect to a central VPC labeled Shared Services VPC in US Central 1. This VPC acts as the hub, providing connectivity between on-premises and other VPCs. The shared services VPC might host common resources like DNS servers that need to resolve host names for both on-premises and cloud resources, authentication services like Active Directory domain controllers, monitoring and logging infrastructure that collects data from all environments, or administrative jump servers used to access resources across multiple VPCs. From the shared services VPC, two VPC peering connections extend to separate tenant VPCs, production VPC and development VPC. These peering connections are represented by dotted lines to indicate their logical connections within Google Cloud rather than physical links. The production VPC might host customer-facing applications, databases, and workloads that must be isolated from development activities. The development VPC hosts testing environments, staging systems, and development workloads that need isolation from production but still require access to shared services like DNS and authentication. The critical configuration that makes this topology work is shown in the note. Export custom routes must be enabled on shared services VPC peering, and import custom routes must be enabled on production VPC and development VPC peering. When you create or modify the VPC peering connection from shared services VPC to production VPC, you enable the Export Custom Routes option on the shared services side. This tells Google Cloud to advertise routes learned via interconnect across the peering connection. On the production VPC side of the peering, you enable Import Custom Routes, which tells the production VPC to accept and install these advertised routes. The same configuration applies to the development VPC peering. With this configuration, when your on-premises LAN advertises the 10.0.0.0/16 range via BGP to the shared services VPC, that route is then propagated across the peering connections to both production VPC and development VPC. Instances in those VPCs can now read your on-premises network by sending traffic to the shared services VPC, which forwards it through the interconnect connection. Similarly, when you create new subnets in production VPC or development VPC, those routes can be exported across the peering to shared services VPC if you enable the appropriate settings, and then the shared services VPC's cloud router can advertise them via BGP to your on-premises network. This hub-and-spoke architecture offers several benefits. You only need one interconnect connection instead of separate connections for each VPC, reducing costs and management complexity. The shared services VPC provides centralized management of routing, firewall rules, and network policies. You can implement security controls and monitoring at the hub that apply to all traffic between on-premises and cloud. However, there are also considerations. All inter-VPC traffic flows through the shared services VPC, which could become a bottleneck. The shared services VPC becomes a critical single point of failure. If it has issues, connectivity to all peered VPCs is affected. You need careful planning of IP address space to avoid conflicts between on-premises ranges and ranges in multiple VPCs. Despite these considerations, the hub-and-spoke pattern is common in large enterprises with multiple VPCs and is a powerful way to architect complex hybrid cloud networks. Interconnect cost optimization strategies. Optimizing the costs of cloud interconnect requires understanding the various cost components and implementing strategies to minimize expenses while maintaining required performance and availability. Interconnect costs can represent a significant portion of your cloud networking budget, especially for high-bandwidth connections or deployments with multiple connections for redundancy. Effective cost optimization doesn't mean choosing the cheapest option. It means maximizing value by aligning your spending with actual requirements and avoiding waste from over-provisioning or inefficient architectures. The cost optimization strategies fall into several categories. Right-sizing bandwidth ensures you're not paying for more capacity than you need. Leveraging committed use discounts can significantly reduce per-month costs for interconnect connections you'll maintain long-term. Optimizing data transfer patterns reduces egress charges by minimizing unnecessary data movement. Consolidating connections where appropriate reduces the number of separate interconnect links you maintain. Using partner interconnect strategically for lower bandwidth requirements can be more economical than dedicated interconnect. Each strategy has trade-offs, and the right approach depends on your specific usage patterns, growth trajectory, and organizational requirements. The diagram presents 7 key cost optimization strategies, each in its own box with specific recommendations. The top left strategy is right-size bandwidth, which advises you to start with smaller bandwidth tiers and scale up as needed, rather than over-provisioning from the start. Many organizations provision 10 gigabits per second connections anticipating future growth, but actually use only 2 or 3 gigabits per second for the first year or two. With Partner Interconnect, you could start with a 5 gigabits per second connection and upgrade when utilization consistently exceeds 70%, saving costs during the lower usage period. The strategy recommends monitoring actual utilization monthly to identify when upgrades are truly necessary, not just provisioning based on theoretical worst-case scenarios. Right-sizing means finding the sweet spot where you have adequate capacity for current needs plus reasonable growth headroom, but aren't paying for excessive unused bandwidth. The top right box covers committed use discounts, which are contracts where you commit to using an interconnect connection for 1 or 3 years in exchange for significant discounts off the pay-as-you-go monthly pricing. For production interconnect connections that you know you'll maintain long-term, committed use discounts can reduce your costs by 25 to 40% or more. The key is being confident in your commitment. There are penalties for early termination. This strategy works best for core connections supporting steady workloads, not for temporary connections or experimental deployments. The recommendation is to start with monthly billing for new connections until you validate they meet your needs, then convert to committed use after a few months of stable operation. The middle left strategy is optimized data transfer patterns, which focuses on reducing egress charges. While interconnect egress rates are lower than internet egress, you still pay per gigabyte for data leaving Google CP through the connection. The strategy recommends reviewing what data is being transferred and whether all transfers are necessary. For example, if you're replicating database transaction logs to on-premises for backup, consider whether you could instead use Google Cloud Storage for backups, eliminating that egress traffic. If you're transferring large datasets for on-premises processing, evaluate whether that processing could be done in Google Cloud instead, keeping the data in the cloud and only transferring results. If you must transfer data, compress it before transmission to reduce gigabyte counts. Sometimes architectural changes that minimize data transfer provide greater savings than optimizing the connection itself. Consolidate multiple connections appears in the middle right box. If you have multiple low bandwidth connections, evaluate whether they could be combined into fewer higher bandwidth connections. For example, if you have 3 separate 1 gigabits per second partner interconnect connections for different applications, you might consolidate them into a single 5 gigabits per second connection using VLAN attachments to maintain logical separation. Consolidation reduces per connection fees, simplifies management, and often provides better per megabit economics. However, consolidation also means less isolation. All traffic shares the same physical connection, so you need to carefully evaluate whether the cost savings are worth the reduced failure isolation. The bottom left strategy addresses leverage partner interconnect for lower bandwidth needs. As we've discussed, Partner Interconnect offers more granular bandwidth options than dedicated interconnect's 10 and 100 gigabit tiers. If your requirements are under 10 gigabits per second, Partner Interconnect is almost always more economical when you consider the total cost including colocation, equipment, and management. The strategy recommends using dedicated interconnect only when you actually need 10 gigabits per second or more, or when you have specific requirements that Partner Interconnect can't meet, such as needing to control every aspect of the physical infrastructure. For branch offices, development environments, and disaster recovery sites, Partner Interconnect usually provides the best cost-to-performance ratio. Review redundancy requirements in the bottom middle box. suggests regularly assessing whether you actually need all the redundancy you have implemented. Many organizations start with fully redundant interconnect configurations for all environments, including development and testing, when that level of redundancy might not be necessary. Consider whether development VPCs need redundant connections, or if a single connection is sufficient given that development outages don't impact production. Evaluate whether you need 4 nines or 5 nines availability for each workload, as the redundancy required to achieve 99.99% uptime is significantly less than for 99.999% uptime. This doesn't mean eliminating redundancy for production. It means being strategic about where redundancy is truly necessary versus where it's over-engineering. The final strategy in the bottom right box is use Cloud VPN for non-critical traffic. Cloud VPN, which tunnels traffic over the public internet, costs significantly less than interconnect both in connection fees and in the fact that you can use smaller, cheaper edge devices. For workloads that don't require interconnect's performance and reliability, such as asynchronous batch jobs, low-priority backups, development environment access, or disaster recovery standby connectivity that's only used during actual disasters, VPN might be sufficient and dramatically cheaper. Some organizations implement hybrid architectures where interconnect carries production traffic and latency-sensitive workloads, while VPN handles everything else. This tiered approach to connectivity can significantly reduce costs while maintaining excellent performance for applications that truly need it. Advanced use cases and best practices. As organizations mature in their cloud interconnect deployments, they often implement advanced patterns and architectures that go beyond basic connectivity. These advanced use cases leverage interconnect's capabilities to solve complex business and technical challenges, create sophisticated hybrid cloud architectures, and optimize for specific requirements like ultra-low latency, massive scale, or regulatory compliance. Understanding these advanced patterns helps you architect more effective solutions and avoid common pitfalls that emerge at scale. Advanced use cases often combine multiple Google Cloud networking features with interconnect. For example, you might integrate interconnect with Cloud Router route advertisements to dynamically control traffic engineering. Combine interconnect with VPC service controls for data security perimeters. Use interconnect with private Google access to read Google APIs without internet traversal. Integrate with Traffic Director for advanced load balancing across hybrid environments, or leverage Network Connectivity Center to manage complex multi-region, multi-VPC topologies. These integrations create powerful capabilities but also increase complexity, requiring careful planning and skilled network engineering. The diagram shows 4 advanced use cases, each representing a sophisticated architecture pattern. The top left box describes multi-region active-active deployments where applications run simultaneously in multiple Google Cloud regions with interconnect connections to each region. This architecture provides both high availability and optimal performance by serving users from the closest region. Your on-premises network maintains separate interconnect connections to US Central 1 and US East 1. For example, using BGP route engineering, you can configure routing so that traffic to US Central 1 resources preferentially uses the US Central 1 interconnect, while traffic to US East 1 resources uses that region's interconnect, minimizing cross-region traffic and latency. The implementation details note that you need careful border gateway protocol configuration using attributes like local preference and autonomous system path prepending to control which connection is preferred for which destinations. Load balancing across regions requires either domain name system-based global load balancing or Google Cloud's application load balancers with anycast addressing. Active-active means both regions are serving production traffic, unlike active-passive where one region is just a standby. This doubles your interconnect costs since you need connections to multiple regions, but it provides the ultimate in availability and performance. If one region fails, the other continues operating seamlessly. If one interconnect connection fails, traffic can still reach both regions through the surviving connection, though possibly with higher latency. The top right box covers disaster recovery with instant failover, a critical use case for business continuity. The architecture maintains your primary production environment on premises with a replicated environment in Google CP that's continuously synchronized. Interconnect provides the high bandwidth, low latency connection required for real-time replication. The implementation uses multiple VLAN attachments, one for normal application traffic and separate attachments for replication traffic, allowing you to prioritize and monitor replication independently. BGP configuration includes specific route advertisements that can be quickly modified during failover events. The replication frequency is continuous for critical databases, using technologies like Oracle DataGuard, SQL Server Always On, or PostgreSQL streaming replication. For file systems, you might use rsync, robocopy, or storage replication technologies. The key is that Interconnect provides sufficient bandwidth for replication to stay current even during peak business hours. In a disaster scenario, you modify BGP advertisements to direct production traffic to the Google Cloud environment, effectively making the cloud your new primary. Users experience minimal disruption, typically just a few minutes of downtime during DNS propagation and connection re-establishment. Once your on-premises environment is restored, you can fail back or continue running in the cloud, demonstrating true flexibility. The bottom left box describes media rendering and processing pipelines, a use case common in entertainment, advertising, and content creation industries. These workloads involve enormous datasets, such as 8K video files that might be hundreds of gigabits per second per video. The files originate on premises where content creators work, but processing and rendering happen in Google CP to leverage massive parallel compute resources. Interconnect's high bandwidth, particularly 100 gigabit dedicated interconnect, makes this feasible. A video file uploads to Google Cloud Storage via Interconnect. Cloud Functions or Compute Engine instances automatically detect the new file and spawn rendering jobs. Hundreds or thousands of virtual machines perform parallel processing, and the completed output transfers back on premises via Interconnect. The implementation uses Google Cloud Storage as the staging area for files entering and leaving the cloud. Transfer jobs are optimized using parallel streams and compression where applicable. Object Lifecycle Management automatically deletes processed files after a certain period to control storage costs. The rendering pipeline uses preemptible virtual machines to dramatically reduce compute costs, since rendering jobs can tolerate interruption and restart. Interconnect bandwidth becomes the bottleneck. A 100 gigabit connection can transfer approximately 12.5 gigabytes per second, meaning a 100 gigabyte video file takes around 8 seconds to transfer under ideal conditions. Real-world transfer speeds are lower due to protocol overhead and other factors, but the point is that Interconnect makes these massive transfers practical where internet-based transfer would be prohibitively slow. The bottom right box presents Internet of Things data ingestion at scale, relevant for manufacturing, logistics, smart cities, and connected vehicle applications. These scenarios involve potentially millions of Internet of Things devices or sensors generating data that must be collected, processed, and analyzed. The architecture uses on-premises edge gateways that aggregate data from thousands of local Internet of Things devices, reducing the volume of data that needs to traverse networks. These gateways connect to regional data centers that further aggregate and pre-process data from multiple edge locations. The regional data centers maintain interconnect connections to Google Cloud where large-scale data processing occurs using BigQuery for analytics, pub/sub for message queuing, Dataflow for stream processing, and Bigtable for time series storage. The implementation leverages Interconnect's consistent performance characteristics, critical when dealing with real-time data streams. The bandwidth requirements depend on your device count and data generation rate. A million devices each sending 1 kilobyte every 10 seconds generates approximately 800 megabits per second of sustained traffic, easily handled by even a 1 gigabit interconnect connection. However, you need to account for peaks when many devices report simultaneously, or when historical data backfills occur. The architecture uses buffering and flow control at each tier to handle temporary spikes without data loss.